ladies and gentlemen. What I'd like to do today is to take a little bit of a detour in which we'd like to continue our discussion of the logarithmic function, and it requires a little bit more background of approximations. So let's look at that and see how it goes. Suppose you were to go down to the local drugstore, for example, and were to weigh yourself, and suppose you weighed 137 pounds, all right? And now, to the nearest pound, this number then must be what? Greater than or equal to, we have already said this once before, I believe, greater than or equal to what number? To the nearest pound, but 136.5, and then it must be less than what number, but Tim?
137.5.
137.5, all right? So then this number to the nearest pound, I think you agree, then must be between these two digits. All right? Well, at the same time, suppose the chemist happened to be weighing some compound there, and suppose he came up with a measurement of 0.137 ounces. And again, to the nearest ounce, if that is his unit of measure that he is dealing with, this then must be greater than or equal to what number? But anyone? 0.1365, and then it must also be less than what number, but Doug? 0.1375. So this measure then is to the nearest what? This then is to the nearest thousandth, is that right? To the nearest thousandth of an ounce. Let's use the unit of measure of an ounce, all right? Now, let's look then at our weight again. And the maximum possible error that we may have, we will take as being 1/2 of the unit of measure that we are dealing with. So that in terms of our pound, which is our unit of measure, 1/2 of that then is 0.5. And this then is our maximum, all right, our maximum possible error that we may have in our measure. And let's look then at our chemist. And the maximum possible error that he may have would be 1/2 of his unit of measure, which is then going to be 1/2 of what number? 0.001. 1/1000, is that right? And then that then is going to be what? 0.0005 is his maximum possible error. All right? Well, then what we think of as the relative error, or the degree of accuracy, is then going to be the ratio of this number, in this case of 0.5, to his actual measurement, which in our case of the weight is going to be over 137. Now let's see what this number is going to be. Let's multiply both numerator and denominator by what number? By 10, and that gives us 5 over 1370. I did some arithmetic before the lesson started, and this turns out to be 0.0036. And if we then were to express this as a percent, this then would be equal to what number? But 0.36%. All right, and we speak of this as as our what? As our relative error. We call this number our relative error, or else another name for it is what we may think of as the degree of accuracy of our original measurement, okay? The degree of accuracy. Well, let's look then at what the chemist's degree of accuracy is going to be. And again, it's going to be this maximum possible error, 0.0005, divided by what number? But by his actual measurement, which in this case is going to be what number? 0.137, okay? Now, let's look at this number, and let's decide to multiply another name for the number 1. Will be, what?
10,000.
Like 10,000, and that then will give us a 5. And let's see, now we moved our decimal point over 1, 2, 3, 4 places. So if we did so here, we have what? 1370. And notice that this number is indeed exactly the same as this number that we have here. Therefore, writing it as a decimal equivalent, it's 0.0036. And again, writing it as a percent, it may be thought of as what? As 0.36 of a percent. And notice now in each case that the relative error is indeed the same number. And even though here we are talking about our unit of measure, which is a pound, and our measure was to the nearest pound, and this was to the nearest thousandth of an ounce, our percentage of error turned out to be the same. Okay? Well, let's see now. I think perhaps there are one or two other ideas that we can talk about. Let me call this our first notion. And suppose we were to talk about significant digits. If I then were to look at the number 0.137, the number of significant digits that we have here indeed will be all three digits. Is that right? Namely the number 1 and the number 3 and the number 7. So we speak of these as our significant digits. So I think this is an idea that certainly you are familiar with. Now, suppose we then were to write 0.0137. And is this first 0 a significant digit as we write it? And I think we'll all agree that it is not. So our significant digits are still 1, 3, and 7. Suppose we were to have 0.01370. And without knowing any more information about this last digit here, this 0, if our measure were, say, to the nearest 10,000th of a unit, would this then be significant? If we then said that our original measure, our relative, rather coming back here and talking about our maximum possible error as being that number, let's take it as 0.000005. And if I took it out to a half of the degree of the measure that we're dealing with, would it then be significant? And I think you would agree that under those conditions it would. But unless you're told something about this 0, this last 0, the trailing 0, so to speak, what is our conclusion that we have come to about those numbers, Bill?
It's not significant.
That it is not significant. So in this case, the only significant digits also are the numbers 1, 3, and 7. Okay? Our first 0 is never significant, and the last one is significant only if you were told so. Well, let's then look at a number such as 0.010370. And how about this digit, this number 0 here? Is that significant? And Doug?
The middle 0.
The middle 0. Is this a significant digit? And I think you will agree that it is. So we have 1 and 0 and 3 and 7 are our significant digits, whereby this 0 that is significant indeed is the one which is between two significant digits. Is that right? Well, again, I think that this should be quite familiar to you. Another idea that I think we can look at is what we think of as scientific notation. And again, I believe that this is one that should be familiar to you. Suppose we were to take, say, the number 137 and write it as 1.37 times 10 raised to some power. And of course, the number, it must be raised to what power? But when? To the second power in this case. Suppose we had the number 1.37. And I think here, if I wrote this as 1.37 times 10 raised to what power? That power must be 0 in this case. Suppose we had 0.0137. And this then, when written as, notice, our numeral here must be a number between 1 and 10. Is that right? 1.37 times 10 raised to some exponent, such that we end up with the number that we started with, Brenda.
To the negative 2 power.
Times 10 raised to the negative 2 power would then give us this number. And we give this name scientific notation. Some people refer to it as this, and some others refer to it as standard notation. And these are names that we give to writing a number in this pattern, in which notice that the generalization would be something such as a times 10 to the n power, where a then is any number between 10 and 1, is that right? And n is over the set of what numbers? N can be any, that exponent can be an integer, is that right? Okay? Well, let's utilize this idea. In fact, this whole idea of scientific notation is going to prove very useful when we come back to look at logarithms. But before we do so, let's look at a very simple problem, which it says estimate the value of this number. And let's use our little dot over the equality symbol to indicate that it is an approximation. Actually, the purpose of a problem such as this is to simply give you some idea of the magnitude of the number that you're dealing with. For example, 4847, you might say is 5 times 10 raised to what power? Writing it in scientific notation, this is certainly closer to 5 times 10 to the third rather than 4 times 10 to the third on the basis of rounding off. And then times, and here we have 23.95, might be the closest name for that is what? How about 2 times what? 10 to the first, and then times, here's 387, the closest name for that, Glenn, is 4 times 10 to the second, divided by, and now let's see, 4768 is closer to some number such as, Rick, 5 times 10 to the, what? To the negative 2 power. Does everyone agree with that? Times 10 to the negative 2. Well, let's then just look at this approximation. 5 over 5 is a name for 1. 2 times 4 is 8 times. And now let's include all of these exponents. We have there a 10 cubed times 10 to the first power times 10 to the second power. And in fact, this is then 1 over 10 to the negative 2, which is times 10 to the second power. And this then is equal to what? Then we have 8 times 10 raised to the 3, 4, 6, 8 power, is that right? And we then have 8 with how many zeros? With 8 zeros, is that right? 1, 2, 3, 4, 5, 6, 7, 8, and that looks like a number around 800 million as a rather rough, certainly, number, which is a name for our original number that we started with. Well, let me give you some of these problems for homework in which you can practice some of these ideas. This will be assignment